That's interesting. My hacking headlamp appears to be pulse width modulated at 480 Hz. Hi, I'm Kevin. Welcome to my cave. In this series, we've been looking a lot at various sorts of op-amp circuits that exist purely to amplify the signal. Usually, what we're after is a linear relation between the input and output. But we've been pretty loose about the definition of what a signal is. Today, I'd like to introduce one classification scheme. Under the scheme I want to propose, a signal is one of two things. It's either a voltage or a current. If a signal is a voltage, we generally want the output impedance of the source to be as low as possible. More to the point, we want the input impedance of the load to be as high as possible. That's because if they don't match in that way, we'll lose a lot of our signal, because the source and the load will form a voltage divider. We often use the rule of thumb of making the input impedance of an amplifier at least 10 times the output impedance of its source. Sometimes in precision circuits, we either want to make it much higher than that, or introduce extra complexity to compensate for the loss. Most of the signal processing circuits work with voltages at both the input and output. Most op-amps have near infinite input impedances, and we've seen in an earlier episode that a properly configured feedback loop has almost zero output impedance. We speak of them as having voltage gain. Voltage gain is a unitless quantity. We divide the change in output voltage by the change in the input voltage, and the units cancel out. Of course, sometimes our signals are currents rather than voltages. In this case, the desired impedances are reversed. We want the source impedance to be as high as possible so that the current stays nearly constant as the load varies, and the load impedance to be as low as possible. Once again, the circuit gain is a unitless quantity. It's the output current divided by the input current, and the units cancel out. Sometimes we want to have a circuit whose output current is proportional to the input voltage. Maybe we need specifically to regulate a current in the outside world, perhaps in an electroplating tank, or in the drive circuit for a laser diode. The performance figure for a circuit like this is the change in output current divided by the change in input voltage. So the units will be amperes divided by volts, or Siemens. Siemens are a unit of conductance. We use the trans prefix because the effect is across the circuit. A voltage in one place becomes a current in a different place, so we call it a transconductance. We're going to see transconductance a lot when we get into field effect transistors, because they're naturally transconductance devices. Sometimes what we have is a source with an extremely high impedance instead of an extremely low one. These sources will emit a tiny current that might require an input impedance that's unrealistically high in order to show a significant voltage. One way we've dealt with these up to now is to buffer them with a BJT. If we limit the biasing conditions, a common emitter amplifier looks like a current amplifier. The collector current is a constant times the base current. So this circuit is an amplifier with current in and current out. Current gain once again is unitless. Once we've boosted the current high enough, we can translate it to a voltage simply by adding a collector resistor. A single resistor to a fixed voltage is a transformer from current to voltage. When we consider the circuit as a whole, the output voltage becomes a linear function of the input current. The units are volts divided by amps, or ohms. And we've referred to the circuit performance figure as a transresistance. This behavior, in fact, is how the transistor was named. The small signal transistor amplifier exhibits transresistance. For various reasons, many engineers prefer to say transimpedance in place of transresistance. But somehow, you never seem to hear the complementary term transadmittance in place of transconductance. I have no idea why. Over in the transistor series, we've learned about any number of problems using a single transistor as a transimpedance amplifier. The fundamental nonlinearity of the Ebers-Moll effect, The early effect and the Miller capacitance are three things that come to mind. The time has come to design a better transimpedance amplifier. Of course, we'll want to use an op-amp and a feedback loop. Let's design one. Before we continue, let me interrupt for just a moment. Longtime viewers of this channel will know that it's always free to all comers. Nothing is ever paywalled. But I do end each video asking one thing, that you take care of one another. To that end, all the advertising revenue that I earn from this channel goes to charity. The current featured charity is called Heifer International. Heifer's mission is to end hunger and poverty in partnership with the communities it serves. It begins with a seed investment in livestock or agriculture, together with mentorship to help its participants build a business. The participants, small farmers, ranchers, and female business owners, are able to earn a living income and continuously lift up their communities as they train the next generation of leaders. I'd like to ask you to join me in supporting this organization. I set a goal of $500, which is enough to give a cow to a family in need, together with training and education in how to care for her and how to access the market for her milk. I know that with the generosity of Kevin's Cave people, we'll just crush that goal. Won't you help out today? There's a link to donate, up here, or down there, or at any rate somewhere nearby. Thanks so much, and now back to the video. For the signal source, I'm going to use a photodiode. This is a device that behaves like an ordinary diode, except that it's sensitive to light. Well, actually, all diodes are sensitive to light. If you're energetic, try a circuit like the one I'm about to show you, using an ordinary glass-encased diode. See if you can see any effect with a strong light. You'll certainly see the effect if you use an LED instead. That's why so many semiconductor devices have cases that block the ambient light. But come on, Kevin, get back to the topic. Don't wander into the weeds. For the photodiode, I'm actually using the base collector junction of a BPV11 phototransistor. We'll look at using it as a transistor later. The photodiode works because when photons hit the semiconductor, they transmit energy to electrons, which can get shaken loose from the lattice and absorbed somewhere else. The resulting electron-hole pair can be on opposite sides of the junction, leaving the electron and hole free to migrate. The cumulative migration results in a current in the reverse direction relative to the diode's orientation. We'll take that current, called a photocurrent, and feed it into our circuit. It'll arrive at the summing junction of an op-amp inverting amplifier. The summing node is virtual ground, and so there will be an extremely low impedance looking into it, which is what we want. We'll use an extremely large feedback resistor, say 10 megaohms. Since we assume the op-amp input draws no current, the current through the feedback resistor will have to balance the current at the input. A 1-volt output will correspond to a 100 nanoamp input, or in other words, the trans resistance will be the same 10 megaohms. That should be enough to see how the circuit responds to light. But before I build it, let me raise one practical detail. There is going to be stray capacitance about. On a breadboard setup like this, it could be more than 10 picofarads. The feedback path will be a low-pass filter. The corner frequency of that filter will be only about 1600 Hz, well below the gain bandwidth product of the op-amp. At some frequency not far above that corner, our negative feedback will be phase shifted to positive feedback, and the circuit will oscillate. We know what to do about that. Add a compensation capacitor. 22 picofarads will give a corner frequency of about 720 Hz, which should kill any oscillation that we encounter. This problem is a general gotcha for circuit designers. There might be enough stray capacitance around the feedback resistor on a breadboard, and then the circuit will fail on a proper PC board. And attaching a scope probe might change the behavior. So let's just add the capacitor as a safety measure. Here's the circuit on the breadboard. It's not much to look at since there's only a handful of components. There's a bit of a mess surrounding it because there are multiple light sources that I want to experiment with. With both the room lights and the desk lamp lit, The output is totally saturated. I'd need to use a smaller feedback resistor to handle this much light. But if I turn off both the desk lamp and the overhead light, the output drops to effectively 0. If I turn one of the lights back on, I can show that the circuit responds as I shade the photodiode with my hand. I really don't like using a 10 megaohm feedback resistor. The op-amp will have some small bias current, and that small bias current will be multiplied by the transresistance and can add up to a significant voltage. What's worse, the bias current will be horribly temperature dependent. Also, that 10 megaohm resistor will contribute quite a lot of Johnson noise. But fortunately, I'm not using just a photodiode. My diode is the base collector junction of a phototransistor. Just like a photodiode, a phototransistor works by having a photon deposit energy near a junction. The energy can shake loose an electron, leaving an electron-hole pair. This time, when the carriers migrate, the hole is migrating to the base emitter junction. That amounts to a conventional current between base and emitter. Transistors still have current gain, so we'll see a much larger current between collector and emitter. A phototransistor therefore outputs a much larger current than a photodiode. It does so at the expense of speed, due in part to the Miller effect. But for a simple photometer, we don't really care. So let's remove the photodiode version and wire the device as a phototransistor instead. We can reduce the feedback resistor by a factor of 100, assuming that the beta of the transistor is at least that great. Now we can look at the response to light in more detail. Now let me try a few light sources. The first one is an old-school fluorescent ring light, not a newfangled LED one. You can see a pretty extreme variation of the light intensity with every half cycle of the power line. The persistence of the phosphor keeps some light present during the zero crossings. A modern LED lamp shows a similar 120 Hz variation, but less extreme, and with a peculiar waveform. I might have to take one apart at some point to see what the power supply looks like. I wanted to show something smoother, so I wanted an incandescent light. The only incandescent lamps I could find in the house were Christmas decorations, so I stole an electric candle from one of the windows. Oops, that bulb's a little too close to keep the output from saturating. There's still a little bit of 120 Hz visible, but the waveform is much more nearly flat than the other two sources. The filament is still hot for the entire cycle and gives off nearly a constant intensity. I was curious what I was going to see with a hiking headlamp, so let's have a look. At full brightness, it's showing almost a DC signal. Whoa, this angle is reflecting right off the scope screen into the camera. Let me try to move it. Okay, that's a little better. At full brightness, I'm seeing almost a constant light intensity. But as I dim it, I can see that it's pulse width modulated at a pulse repetition rate of 480 Hz. Dimming it further gives narrower pulses. And of course, brightening it again gives wider ones until they merge to a continuous light again. Finally, I want to see what happens with a really stable light source. So I wired up a few tiny incandescent bulbs in series, running off DC from my pinched power supply. The output from the circuit is pretty much flat, as you'd expect. So here, we've managed to design a photometer from scratch. What might such a thing be good for? Maybe you'd want to measure whether you're delivering enough light to cure UV-sensitive epoxy. Add an integrator and a comparator to our photometer, and you have the basic circuit. Or perhaps you want to build the receiver for a remote control. That would need some sort of photometer at the front end. I bet you could monitor the concentration of some colored chemical in solution. I'll let you think of other things you could use a photometer for. I've got a couple of fun ideas, but they'll have to wait for another video. I hope you'll stay tuned, and perhaps tell YouTube that you want to hear when my next video drops. Until then, stay safe, stay healthy, stay curious, and please take care of one another. Bye!